So I want you to just take a second and imagine standing at the edge of this completely pristine mountain lake.
Oh, that sounds pretty nice right about now.
Right.
Yeah.
It's gorgeous. The air is super thin, it's crisp, the water is just totally transparent, and you're standing exactly 854 meters above sea level in these really rugged mountains in Norway.
That is a serious hike.
It is. And the time is roughly 8,000 or 9,000 years ago. So this is not long after the massive glaciers of the last ice age have finally, melted away.
Right, a very raw landscape.
Exactly. And because of how high up you are, and because the rivers leading to this lake are just choked with these massive impassable waterfalls, there are no fish here.
None at all.
Right. I mean, it is physically impossible for fish to migrate up into this sort of biological penthouse suite, if you will.
Yeah, there is no elevator up to the penthouse.
No elevator. But if you look at the archaeological timeline and you fast forward just a little bit, suddenly this exact same lake is absolutely teeming with massive calorie-rich brown trout.
It's incredible.
It really is. It's basically a prehistoric locked room mystery. Like, how on earth did the fish get in?
It really is a locked room mystery. But, the answer to that mystery actually changes everything we thought we knew about early human history.
Wow, everything.
Pretty much, yeah. Because when archaeologists recently drained that specific lake, they didn't just find ancient fish bones. They found a massive 7,000-year-old wooden machine just buried right there in the mud.
A wooden machine.
Yeah, and what they found completely shatters our traditional understanding of early human ecosystems. I mean, for a really long time, the neat, tidy historical narrative has always been that agriculture was the starting point for human environmental management.
Right, like farming is when we started controlling things.
Exactly. But the discovery at this site, which is called Lake Tesse, by the way, it proves that thousands of years before the invention of farming in this region, these so-called simple hunter-gatherers were actually acting as highly sophisticated environmental engineers.
I love that. So our goal for today's deep dive is to unpack this whole stack of recent archaeological research on these Lake Tesse fire apps.
Yeah, and it is a wild ride.
Okay, so to even understand why human intervention was necessary in the first place, we have to look at the extreme geography of these Norwegian mountains. I mean, put us in that post-glacial landscape. The ice has just melted. What are we actually looking at?
Well, for most of the last glacial period, which ran roughly from, 115,000 to about 9,700 BC, inland Norway was completely crushed under the Fennoscandian ice sheet.
Wow, okay.
Yeah, we are talking about ice up to 3 kilometers thick in some places.
3 kilometers? That's insane.
It is, and the sheer weight of that ice actually depressed the Earth's crust. It physically pushed the land down.
Right, I've heard of that.
So as the global climate warmed, this ice sheet gradually retreated. And by about 8,000 to maybe 8,400 BC, the central mountainous region of southern Norway, an area known as Jotunheimen, it finally opened up.
So the ice melts away,
Yeah.
and what's left?
It leaves behind this incredibly scarred landscape. You've got deep valleys, really steep, erratic rivers, and high-altitude lakes like Lake Tesse.
Okay, so water is basically flowing everywhere as this ice melts. Rivers are forming. Now, I have to play devil's advocate here.
Go for it.
Fish are incredibly resilient, right? They're opportunistic. Why wouldn't they just colonize these new rivers and swim upstream as the waterways establish themselves?
It's a fair question, but it comes down to a geological concept called the marine limit, combined with just the extreme topography of the area.
The marine limit?
Yeah. During the early Holocene, as the ice retreated, relative sea levels in that region were very, very high.
Right.
Because remember, the land was still compressed from all the weight of the ice.
Oh, right. So the water can just come further in.
Exactly. Ocean water flooded much further inland than it does today. So fish naturally and easily colonized those lowland waterways. They just migrated in from the coastal zones and the Baltic Sea.
That makes sense.
But there is a hard limit to how high that sea level goes and how far inland the ocean can actually reach. The marine limit in this specific region was around 180 meters above present sea level.
Wait, 180 meters. But earlier I said Lake Tesse is sitting at 854 meters above sea level.
Yes, it is.
So that is nearly 700 vertical meters of separation.
Exactly. So the lowland rivers were full of fish, sure, but the high-altitude watercourses were completely cut off. The topography created by the glacial carving was just too extreme. We're talking about incredibly steep gradients and massive rushing waterfalls.
Just sheer cliffs of water.
Right. These served as absolute impassable topographical barriers. Now, a brown trout is a powerful swimmer, for sure, and they can leap small cascades, but they absolutely cannot swim up a sheer cliff of falling water.
Right, they aren't superheroes.
No, they aren't. So, naturally, these upper lakes just remain completely devoid of fish.
Okay, hold on though. I want to challenge this premise that swimming was the only way in. If we are looking at a sterile mountain lake that suddenly has fish in it, couldn't they have just been dropped from the sky?
Dropped from the sky. You mean by birds?
Yeah, birds. We know avian transport is a real biological phenomena. Like an osprey catches a fish down in the lowlands, flies over the mountains, and just accidentally drops it.
Or wading birds tracking sticky fish eggs on their feet.
Exactly, from a lower lake up to an upper lake. Doesn't that explain the sudden appearance of trout without needing, humans to carry them up there?
Well, avian transport of fish or fish eggs across dry land does exist in theory, yeah. And biologists have actually debated its frequency for decades. But when researchers apply that specific theory to the Norwegian mountains, the mechanics of it completely fall apart.
Really? Why?
First, just consider the chaotic nature of biological dispersal via birds. If birds were randomly dropping live fish or tracking fertilized eggs on their webbed feet, you would expect this sort of biological lottery.
Right, like a total mix.
Exactly. You would get a random mixed assortment of whatever fish species existed in the lowlands ending up in these high mountain lakes. You'd see pike, perch, char, trout, all just mixed together.
Because, a bird doesn't care what species it accidentally drops. It's just totally random chance.
But random chance is not what the archaeological and biological records show here at all. Historically, there was only one highly specific species found in these upper mountain lakes, and that is the brown trout, or Samochuta L.
Just the brown trout.
Just the brown trout. This kind of strict, species-specific monoculture is virtually impossible to explain through the chaotic mechanism of bird droppings. Natural dispersal would be messy,
Yeah.
This distribution is surgically precise.
Wow, okay, so the precision pretty much rules out the birds.
It really does.
Yeah.
Furthermore, when researchers analyze the broader archaeological data across Scandinavia, specifically looking at the burned fish bones found in the hearths of various mountain camps, they see this synchronic emergence of mountain fishing.
What do you mean by synchronic?
The appearance of trout in these high-altitude lakes kicks off almost everywhere right around 5000 BC.
Oh, wow. All at once.
All at once. If birds were seeding the lakes, it would happen randomly and sporadically over thousands and thousands of years. A sudden, simultaneous explosion of a single species across an entire mountain range strongly points to a deliberate, coordinated, human-driven spread.
Man, that really forces you to confront the caloric economics of what these ancient people were actually doing. In 5000 BC, every single calorie burned is literally a matter of life and death.
Absolutely.
So to expend thousands of calories hauling dead weight, like heavy containers of water and live fish up a 30-degree mountain gradient past waterfalls over 800 vertical meters. That is an insane evolutionary gamble.
It is.
Like, this wasn't just a leisurely hike. This was a monumental, grueling transfer of biomass up a mountain.
It's a staggering investment of physical labor and foresight, but knowing they hauled those fish up the mountain, well, that sets the stage. The real breakthrough came from figuring out how they harvested that investment.
Because you have to get them back out.
Right. Introducing apex predators to a sterile lake is one thing. Catching them efficiently enough to justify the caloric cost of putting them there in the first place is another entirely.
Right, and we know they caught them because they left the equipment behind. But this is what I don't get. If they used organic materials, wood, saplings, branches, how on earth did the evidence survive 7,000 years in a lake without just rotting away completely?
Wood survival basically comes down to the specific chemistry of the lakebed. Under normal conditions, if a tree falls in the forest, fungi, bacteria, insects, they break down the cellulose and lignin very quickly.
Right, it rots, like in a few years.
Exactly, it rots. But when wood is driven deep into the mud at the bottom of a cold mountain lake, it enters what we call an anoxic environment.
Anoxic, meaning no oxygen.
Right, there is almost zero dissolved oxygen in that really dense mud. The organisms that usually cause decay just cannot survive without oxygen. So the wood is essentially frozen in time, chemically preserved by the very water and mud that buried it.
So it just sits there in a dark, cold, oxygen-free vault for 7 millennia.
Until human infrastructure changed the landscape again.
Oh, right. Modern times.
Yeah, back in the 1940s, Lake Tesse was transformed into a hydropower reservoir. And as part of managing that power grid, the water level is artificially lowered every single spring.
Oh, so it drains out.
Yes, this annual draining acts like an artificial drought. It exposes these extensive areas of the formerly submerged lakebed. So during one of these low water periods in 2022, a team of archaeologists who were surveying the newly exposed mud spotted something incredible in the southwestern part of the lake.
They just saw ancient wooden poles poking up through the dredged mud.
Literally just sticking out. And when they began to carefully excavate the surrounding mud, they realized they hadn't just found a few discarded sticks. They unearthed 4 distinct, incredibly well-preserved prehistoric fish traps. They labeled them traps 1, 2, 3, and 5.
Okay, the sources we read for this deep dive go into obsessive detail about Trap 5. And we aren't talking about like a woven basket someone just tied to a rock and tossed in the water. This is a full-blown architectural marvel. What did Trap 5 actually look like?
Trap 5 is a total masterclass in prehistoric engineering. When the archaeologists cleared the mud, they found 46 preserved wooden poles.
46.
Yeah, and 40 of these poles were driven into the lake bed in a distinct pattern that outlined a circular chamber roughly 3.5 meters in diameter.
Wow, that is a massive enclosure. That's over 10 feet across.
Exactly. And the remaining 6 poles were arranged leading away from the chamber to form a guiding fence. So essentially a funnel designed to intercept fish swimming along the shoreline and direct them straight into the main trap.
What really stands out to me here is the fragility of the materials they used. We were talking about pre-Metal Age societies. They didn't have steel axes. They didn't have saws. The poles they used were mostly Scots pine, mixed with a little birch and willow, I think.
Right.
But the average diameter of these poles was just 37 millimeters. That is barely 1.5 inches thick. They're building a massive structure out of tiny saplings.
They're using the stems of young trees, which makes total sense given their tools. I mean, felling a massive oak with a stone axe takes days, right? Harvesting saplings takes minutes.
Good point.
So the builders drove the majority of these thin poles vertically straight down into the firm clay beneath the loose lake mud. These vertical poles basically acted as the skeleton. And then, in between these poles, they would have woven a lattice wall, a barrier made of even thinner, flexible branches or twigs, likely willow.
That lets the water through.
Exactly. This woven wall design allowed water to flow through freely, but the gaps were way too small for the large trout to escape.
Okay, but if you build a wall underwater out of thin twigs, you are fighting the physics of water pressure. Currents are strong. Storms agitate the lake. A large, thrashing brown trout weighs several kilograms. If you just stick thin saplings straight down into the mud, the lateral force of the water and the fish is going to just snap them or push the whole structure over. How did they reinforce it?
The builders actually anticipated that exact structural failure. They didn't just use vertical poles. Of the 46 poles in Trap 5, 11 of them were deliberately driven into the lakebed at a 30 to 45 degree angle.
So they angled them.
Yes. These angled poles acted as structural buttresses. They were positioned on the outside of the chamber, leaning inward to support the vertical walls, counteracting the outward pressure of the trapped fish and reinforcing the entire structure against the lateral drag of the water currents.
That is amazing. They're using diagonal bracing. They literally understood the vectors of force underwater and built a reinforced retaining wall.
They really did.
And the manual labor required to do this is astonishing. The researchers documented deliberate cut marks on the wood. They saw signs of the wood being cleaved and split perfectly down the middle, and potential traces of lashing where they might have tied the joints together. Processing 50 pine saplings, sharpening the ends, and driving them deep into a freezing, muddy lake bed using only greenstone axes and human muscle. I mean, that is a massive, coordinated effort.
It is a serious investment of time and community resources. But, as you brought up earlier, finding old wood is one thing. Confirming that this wood predates agriculture by thousands of years requires an entirely different level of proof.
Right.
I mean, how do we know this wasn't just built by a Viking 1,000 years ago, or maybe a medieval farmer?
Yeah, so we need to talk about how we read the clocks hidden inside rotting, waterlogged wood. Because the researchers didn't just use standard radiocarbon dating, right? They used a technique called radiocarbon wiggle matching.
Yes, wiggle matching.
Now, I know standard radiocarbon dating measures the decay of carbon-14, but it often gives a really fuzzy window, sometimes with a margin of error of a few centuries. How does wiggle matching give us a more precise barcode of time?
To understand wiggle matching, you first have to understand why carbon-14 fluctuates in the first place. Carbon-14 is a radioactive isotope created in the upper atmosphere when cosmic rays from space collide with nitrogen atoms.
Okay, with you so far.
Living things like trees absorb this carbon-14 while they are alive. Once they die, the carbon-14 slowly decays at a known constant rate. The problem is that the amount of cosmic rays hitting the Earth isn't constant. It actually changes based on solar activity.
Like solar flares and stuff.
Yeah, exactly. When the sun is very active, its magnetic field shields the Earth, and less carbon-14 is produced. When the sun is quiet, more cosmic rays hit the atmosphere, and more carbon-14 is produced.
So the starting amount of carbon-14 in the atmosphere is constantly wobbling up and down over the centuries based on what the sun is doing.
Exactly. And scientists have spent decades mapping these historical wobbles by testing the carbon-14 levels in thousands of consecutive tree rings from incredibly old trees, things like ancient bristlecone pines and preserved bog oaks.
Wow.
Yeah, and this creates a master calibration curve. It's a highly detailed year-by-year graph of the carbon-14 fluctuations, or wiggles, over the last 10,000 years.
Okay, so how does that apply to the tiny saplings at Lake Tesse?
Well, instead of just testing one chunk of wood from the fish trap and getting a broad date, the researchers take multiple radiocarbon samples from a sequence of known tree rings from the exact same pole. So they test ring number 5, ring number 15, and ring number 25.
Oh, I see.
By seeing how the carbon-14 levels fluctuate across that specific sequence of rings, they get a unique pattern of wiggles. They then take that pattern and basically slide it along the master calibration curve until it locks into place perfectly.
They are literally matching the unique solar radiation fingerprint of that specific tree's lifetime to the master timeline of the Earth's atmosphere.
Exactly. And by applying this wiggle matching to the outermost rings of the poles, which is the wood that formed right before the tree was chopped down, they totally eliminated the wide margins of error. They placed the traps securely and undeniably in the late Mesolithic era. Trap 5 dates to around 4950 BC. And Trap 2 dates to around 5000 BC.
That puts a firm, undeniable pin in the timeline. But they didn't stop at radiocarbon dating. They applied dendrochronology tree ring dating, but they did it at a microscopic level that is just hard to wrap your head around.
It really is.
Because you mentioned earlier that when you pull 7,000-year-old wood out of a lake, it is chemically preserved by the water.
Yeah.
But if you take it out of the water to study it, doesn't it just disintegrate?
It does, yeah. The cellulose structure of the wood is heavily degraded. It is essentially a super fragile sponge where water is the only thing holding the cellular walls up. The moment the water evaporates, the surface tension collapses the cells and the wood just shrinks, cracks, and crumbles to dust.
So how do you even look at the rings?
To measure the tree rings, the researchers first had to chemically replace the water without altering the physical structure of the wood. They used a specialized resin called G-Stab 5050.
G-Stab 5050, catchy name.
Very catchy. They soak the wood in this resin, which slowly displaces the water at a cellular level and then hardens. So it essentially turns the fragile, waterlogged sponge into a solid block of plasticized wood.
Okay, so once it is stabilized in the resin, how do they actually read the rings? Because these are tiny saplings, not giant redwoods.
They used an instrument called a sliding microtome. Imagine an insanely precise, razor-sharp deli slicer designed for laboratory samples.
Wow.
They shave off layers of the stabilized wood so thin that light can actually pass right through them. And the rings they found were astonishing. Some of these tiny poles, which averaged just 37 millimeters across, contained up to 110 individual tree rings.
Squeezing 110 years of growth into an inch and a half of wood, I mean, that means those trees are growing at an agonizingly slow pace.
Which is exactly the biological response you expect from a tree growing in a harsh, cold, high-altitude mountain environment with incredibly short summers.
Right. They barely have time to grow each year.
Exactly. And the rings are so microscopic that standard optical microscopes just weren't enough. The researchers utilized high-resolution computed tomography, or CT scans, to measure the tree ring widths. They were measuring the compressed cell walls down to a resolution of 14 to 25 microns.
Wait, hold on. A micron. Let's put that in perspective for you listening. A single human hair is roughly 70 microns thick. You were telling me they are reading seasonal biological changes in wood that are thinner than a human hair in a sapling that has been rotting in anoxic mud for 7 millennia.
It is a total triumph of archaeological science.
What?
And by zooming in that closely, they discovered a detail that tells us exactly how these ancient humans organized their lives. They looked at what's called the waney edge.
The waney edge, what is that and what does it tell us?
The waney edge is the absolute outermost layer of the wood. It's the very last ring of cells right under the bark. It represents the final season of growth before the stone axe hit the trunk.
The moment of death.
Essentially, yes. To understand why this matters, you have to know how a tree grows. A tree doesn't grow uniformly all year. The growth happens in a layer just under the bark called the cambium. In the spring and early summer, when water is plentiful and the sun is out, the tree grows rapidly. It creates large cells with thin walls to transport water up to the leaves. This is called early wood, and it looks light and porous.
Okay, early wood is spring.
Right. And then in the late summer and fall, growth slows down, creating smaller, denser cells with thick walls to provide structural support. This is called late wood, and it looks dark and dense. Then, in the winter, the tree goes dormant and stops growing completely.
So by looking at the veiny edge under the CT scanner, they can see exactly what type of cellular structure was forming at the moment the tree was cut down.
Exactly. They analyzed the veiny edges of the preserved poles, and out of the samples where the outermost edge was intact, 19 poles ended in early wood and 18 poles ended in late wood.
And the rest?
None of them showed a completed late wood band followed by dormancy. This cellular evidence tells us definitively that the trees were chopped down starting from the cambium's dormant period right through the early growing season. So in simple terms, they were felled in the spring and early summer.
Man, this gives us a hyper-specific window into their seasonal schedule. They didn't just wander past the lake in the autumn and decide to build a trap on a whim.
No, not at all.
They had a structured, deliberate rhythm. They arrived at Lake Tesse in the spring, chopped the wood during the early growing season, built the traps, and then used them to harvest trout all summer long.
It reveals profound intentionality. These traps were not disposable pop-up tents you just leave behind after a weekend forage. They were vital community infrastructure.
The idea of community infrastructure implies permanence.
Yeah.
And the science proves that this wasn't just a one-generation project, right? Like, they maintained these structures for centuries.
We know this for a fact because of the absolute dating achieved on Trap 1. Now, Trap 1 is younger than the others. It belongs to the later Neolithic period. Because the preservation was slightly different, they were able to correlate the tree rings from Trap 1 with a master pine chronology from central Scandinavia, giving them absolute calendar years.
Okay, and what did that show?
The dendrochronological analysis proved that two different poles in the exact same trap 1 were erected about 12 years apart.
12 years.
Yep. One pole was felled around 2669 BC, and a replacement pole was added to the same structure around 2657 BC.
A 12-year gap in construction means these specific bands of people were returning to the exact same bay in the exact same mountain lake decade after decade to repair and maintain their specific traps. Yeah. They were passing the knowledge, the location, and likely the stewardship of these traps down through generations. This just paints a picture of a society deeply rooted to specific coordinates on the map.
It completely shatters the illusion of the perpetually wandering nomad. But, if we pull back and look at the whole system, building and maintaining the trap was really only the final step. To have fish to catch in a sterile lake in the first place, they had permanently altered the local food chain.
Yes, let's get into the mechanics of that biological engineering. We established that humans had to move the fish. But practically speaking, how do you move live trout up an 800-meter vertical mountain pass in 5000 BC? I mean, if you just seal a trout in a leather bag, it's going to consume all the dissolved oxygen in the water and suffocate in 10 minutes.
The logistics of translocation really require a deep understanding of fish biology. We know from the genetic diversity of modern Norwegian mountain trout that this wasn't just a one-time accident where a single bucket of fish was dumped.
It wasn't just a lucky strike.
No, the genetic markers show it was done multiple times as a stepwise process, moving populations progressively upstream through interconnected river systems over decades or even centuries.
But the physical transport mechanism itself, they didn't have aerated plastic coolers. How do they do it?
The archaeological consensus is that they used water skins. Hike processing was a foundational skill in Mesolithic Norwegian life. They were experts at treating animal skins with fats and brains to make them waterproof for clothing, tents, and liquid containers.
Okay, that makes sense.
So it is highly probable they fashioned sealed or semi-sealed water skins to transport live fish or potentially fertilized fish eggs.
Even so, how do you keep the fish alive in a sealed skin on a brutal hike?
You leverage the temperature. Cold water holds significantly more dissolved oxygen than warm water. By transporting the fish in the early spring using freezing snowmelt, they maximized the oxygen capacity of the water.
Oh, that is incredibly smart.
And furthermore, they couldn't just hike straight up. They would have had to make frequent, strategic stops at intermediary streams or pools to open the water skins, aerate the water, and refresh the oxygen supply before continuing the climb. It required a detailed logistical map of all the water sources along the route.
They were essentially managing a biological life support system while scaling a mountain.
Exactly.
And once they finally reach Lake Tesse and pour those surviving fish into the sterile water, they can't even eat them yet. By introducing the brown trout, they're fundamentally rewiring the aquatic food web. But the payoff isn't immediate.
It is the ultimate delayed return economy. Brown trout are large, calorie-rich predators. Once introduced into a lake with no competition, they will feast on the aquatic insects and crustaceans and eventually dominate the ecosystem. But biological populations take time to establish a sustainable biomass. If you drop 20 traumatized fish into a 12-square-kilometer lake, you cannot start heavy trapping the next day or even the next year. If you harvest them too early, the population crashes, and your massive caloric investment is totally wiped out.
So they were essentially treating the lake like a massive high-altitude battery. You charge it with a tiny initial input of live fish. Then you lock the battery away and let biological reproduction act as the current over several decades, storing up thousands of pounds of kinetic harvestable energy for the future.
That is a great way to look at it.
The people who carried those first fish up the mountain in water skins likely never saw the full bounty of their labor. They were planting an underwater garden for their grandchildren to harvest.
And that concept, the delayed return economy, is usually strictly associated with agricultural societies planting crops for the next season. Seeing it applied to a wild ecosystem by Mesolithic foragers requires immense foresight, community planning, and a deep multi-generational understanding of ecology.
It's just wild.
It forces us to ask the ultimate question regarding human motivation. Why go through the trouble? Why incur the massive caloric debt of carrying fish up a mountain only to wait decades for the payoff when you could just stay in the lowlands where the fish already naturally exist?
Yeah, what is the environmental pressure driving this extreme high-altitude risk? Why are they up there?
The answer actually lies in the terrestrial biology of the mountains. The high altitudes were prime hunting grounds for big game, specifically elk and reindeer. We have concrete archaeological evidence of this from sites like the Langfon Ice Patch, which is located just 11 kilometers away from Lake Tesse.
Wait, why are humans hunting near ice patches?
Because the reindeer use the ice patches as a refuge. In the summer, massive swarms of botflies torment the reindeer herds.
Oh, that sounds awful.
It is. So to escape the heat and the insects, the reindeer deliberately migrate up to the perennial ice patches. The ancient hunters knew this. The ice patches made the herds predictable. We have found ancient arrows, scaring sticks, and hunting blinds melting out of the Langfon ice, proving humans were hunting reindeer there continuously since at least the 5th millennium BC.
Wow.
And big game hunting provided enormous amounts of meat, marrow, and crucial hides for survival.
But relying on high-altitude reindeer hunting is a terrifying caloric gamble. I mean, the mountains are unforgiving, the weather can turn violent in an hour, the migration routes of the herds can shift unpredictably. If you march your hunting party up to the ice patch and the reindeer don't show up, or a blizzard pins you down, you are stranded in a barren environment with 0 calories. You face starvation very quickly.
It is a high reward, but catastrophically high-risk endeavor. But by seeding these high-altitude lakes with trout, the ancient hunters were fundamentally altering that thermodynamic risk equation. They were building an ecological safety net. They turned a dangerous, unpredictable hunting expedition into a secure, biologically engineered environment.
Oh, I see. If the reindeer don't show up, the hunting party doesn't starve because they have a guaranteed, highly nutritious, easily harvestable staple food swimming in the lake right next to their camp.
Exactly. They effectively took the harsh, unforgiving mountain environment and biologically terraformed it. They engineered it into a manageable lowland-style habitat where they could safely spend longer periods of time without the constant threat of caloric deficit.
It is landscape-scale risk mitigation. And this revelation, this intentional, multi-generational ecological engineering, the delayed return economy, the massive structural traps, this is the part that demands we rewrite the textbooks on early human sociology, because it completely shatters the rigid paradigm of how we view hunter-gatherers versus agrarian societies.
It breaks the binary that has dominated anthropology for a century. The traditional view categorizes human history into 2 distinct phases. On one side, you have hunter-gatherers who are viewed as passive searchers.
Right, just wandering around.
Exactly. The assumption is they wander around the landscape, eating what nature happens to spontaneously provide, acting as mere participants in the ecosystem, and moving on when local resources are depleted. And then on the other side, you have agrarian farming societies who are viewed as the active producers. They're the ones who manipulate nature, clear land, plant seeds, and exercise control over their environment.
But this discovery at Lake Tesse takes a sledgehammer to that dividing line.
Yeah.
Here is the undeniable timeline. These incredibly sophisticated fish traps and the massive biological engineering project of moving the trout, they predate farming in this region by over 1,000 years. Agriculture didn't even arrive in this part of Scandinavia until roughly 3900 BC, and even then, foraging remained the dominant lifestyle until about 2200 BC.
The people building these traps in 5000 BC were, by definition, hunter-gatherers. But they were utilizing the foresight and environmental control of agricultural producers. This places them in a nuanced category that modern anthropologists increasingly refer to as low-level food producers.
Low-level food producers. I like that.
And Lake Tesse is not an isolated incident. The sources highlight that this is part of a growing, undeniable body of evidence showing how prehistoric foragers actively managed and manipulated their worlds.
Yeah, we aren't just talking about fish. The scale of human intervention goes back much further. Humans were intentionally moving domesticated dogs across continents 15,000 years ago. They deliberately introduced mountain hares to the remote island of Gotland in the Baltic Sea around 7000 BC.
Which is essentially stocking an island with a self-replicating food source to improve their hunting yields.
Exactly.
They also actively shaped the flora. They helped spread hazel trees across northern Europe because the nuts were a crucial, storable staple food, and the flexible wood was perfect for manufacturing tools.
Tools like the lattice walls of the fish traps we just talked about.
Exactly. Furthermore, they were heavily engaged in pyroculture. They used fire to actively manage vast tracts of forest, deliberately burning away dense underbrush to create open clearings.
Now, why would they burn the forest? That seems counterproductive.
Well, because clearing the underbrush actually promotes the growth of fresh, green shoots and grasses, and that, in turn, ungulates the elk and reindeer that they wanted to hunt.
Ah, so they were baiting them.
They were using fire to curate the grazing conditions of wild herds. What all of this points to is that these Mesolithic people possessed deep, highly technical, traditional ecological knowledge.
They weren't just passing through nature as passive tourists or desperate scavengers. They were deliberately cultivating it, managing its biology, and engineering its structure. It really forces us to categorize them as early environmental managers. They mapped the levers of the ecosystem, understood the biological inputs and outputs, and they were pulling those levers to ensure their long-term survival over millennia.
It completely elevates our respect for the intellectual complexity of these ancient societies. I mean, they had the observational science to understand fish biology, the engineering skills to construct hydrodynamic traps, and the generational patience to literally reshape the biological reality of the world around them.
So let's just look at the epic scale of what we've uncovered here today. We started with the geological barrier. Massive waterfalls cutting off the high mountain lakes of Norway as the 3-kilometer-thick ice sheet retreated. We then saw how, starting around 5000 BC, Mesolithic humans decided to solve that topographical problem.
Right.
They calculated the caloric economics, packed live brown trout into aerated water skins, and lugged them up steep, treacherous mountainsides. They possessed the multi-generational foresight to treat that lake as a biological battery, waiting decades for those fish to breed and dominate the ecosystem, basically mitigating the deadly risks of high-altitude reindeer hunting.
It's just brilliant.
And they used advanced prehistoric engineering, understanding water pressure and vectors of force, to build highly precise wooden fish traps out of hundreds of perfectly angled pine saplings. And then they passed the knowledge, the location, and the maintenance of those traps down through their families for thousands of years.
And you know what is truly beautiful about this story? It's the sheer genetic continuity. The legacy of that specific Mesolithic environmental engineering project didn't fade away when agriculture finally arrived. The impact persisted into the Neolithic period, through the Bronze Age, the Viking Age, the Middle Ages, and right up to the modern era.
That's incredible.
If you go to Lake Tesse today as a modern sport fisher, and you cast your line into that freezing mountain water, the brown trout you pull out is the direct, unbroken genetic descendant of the fish those ancient hunter-gatherers carried up the mountain in a hide bag 7,000 years ago.
The past is literally still swimming in that lake, unaware of the millennia that have passed. And that, I think, brings us to our final thought for this deep dive. We've spent this entire time dissecting how these ancient people actively engineered and manipulated their ecosystem to survive. And it leaves you with a profound, slightly mind-bending concept to really mull over.
Oh, definitely.
When you and I look at nature today, especially in remote regions, we have this deep romanticized idea of the untouched, pristine wilderness. We view it as a landscape completely devoid of human influence. But pre-agricultural humans were fundamentally terraforming, burning, seeding, and biologically engineering their environments 7,000 or even 15,000 years ago. How much of what we call untouched wilderness today is actually just the overgrown, wildly successful, and forgotten garden of our ancient ancestors?
It drastically changes how you look at a dense forest, an isolated island, or a high mountain lake. It suggests that human fingerprints have been woven into the very fabric of the landscape for far longer and far more deliberately than we ever dared to imagine.
It definitely changes the view for me. I want to warmly thank you, our listener, for joining us on this incredible journey up the mountain, into the mud, and back in time. We hope you enjoyed this deep dive into the prehistoric mysteries of Lake Tesse. Until next time, keep questioning the world around you, and we'll catch you on the next one.